Okay, make sure you write the definitions down of what a bond is and what the bond energy is. The bond energy is energy required to break a bond. So a single bond will actually be easier to break than a double bond. And then there are even triple bonds that are even stronger, so even more energy would be required to break those. And ionics actually are the strongest to break, the hardest to break. Okay, electronegativity is really going to help us understand a lot of what we're going to be doing in this chapter. This is the lowest. If you look on page 429 or have the handout, these values down here are like 0.47 or 0.7, and up here the value is 4. No units on it. And so that tells us that this is the highest electronegativity, this is the lowest, and it increases up and over. And again, that has to go with the idea of the smaller atom being able to hold those electrons in really tightly and attract other electrons. Okay, when two atoms have a big difference in electronegativity, there's no contest who takes them and who gets them. So what's going to happen is metals, if you look at the periodic table, to the left of the stair-step line, are going to have low electronegativity, and nonmetals to the right of the stair-step line, over to the upper right-hand corner, are going to have high electronegativity. So the electron is going to be transferred because this is so much better at attracting electrons. And so you're going to get a full positive and a full negative, and that's ionic between a metal and a nonmetal. So ionic bonds, it's between a metal and a nonmetal, and that's really what you're going to want to look at the periodic table to identify an ionic bond. Metals will lose an electron to become positive, nonmetals will gain to become negative. That's going to be our biggest criteria. Now, there is usually a big difference in electronegativity. So you'll notice that like cesium and fluorine are 0.7, and fluorine is a 4. So if you subtract that, you get 3.3. That's a huge difference. Because nonmetals tend to have the big electronegativities, metals have the small ones, so the nonmetals take and the metals give. However, they're transferring so that both metal and nonmetal have a noble gas configuration, 8 valence electrons. So as an example here, oxygen has a value of 3.5, K has a value of 0.8, the difference is 2.7. Now, don't just look at those differences, we're actually just going to generalize. If you look at a metal and a nonmetal, it's going to be ionic. Now, on the other end of the spectrum, we have two nonmetals. That's going to be huge for covalent. And if they have the exact same electronegativity values, then neither is able to take from the other, so they share completely equally. Now again, they're going to share to achieve a noble gas configuration, but they're sharing. They're not going to have to transfer. So if you had a bond in the HH molecule, you would see that they're both hydrogens, so they both have a value of 2.1, so the difference is 0. If you look up boron and astatine, I think they're both like 2. So they don't have a difference. So if you have 0 difference in electronegativity, you have what's called a covalent or purely covalent bond, but it's going to be between two nonmetals. Now, of course, those are two ends of the spectrum. You can also have something called a polar covalent bond, meaning two nonmetals that are sharing electrons but not sharing them equally. So they're not transferring, okay, but they're not sharing equally either. This again is covalent, so two nonmetals. So if you look at H and F, those are two nonmetals. They have a difference, so they're not ionic because they're two nonmetals, but they're not sharing equally at all either. So, and then you could look up the values for Si and Cl, and you're going to find that Cl, I think, has a value of 3. I can't remember what Si has, but there's a difference there. So we're going to say that that bond is polar, a polar covalent. Now, the bigger the difference in electronegativity, the more polar the bond is, until it gets to the point that it's such a big difference that it just goes to ionic. But let's take a look at all of these polar bonds. Well, this one's nonpolar, but the difference between carbon and fluorine, carbon is 2.5, fluorine is 4, difference of 1.5. Obviously, the difference between the two H's is 0. N and F, N has a value of 3, F has a value of 4, has a difference of 1. So the most polar bond here is CF, followed by NF, and then, of course, the least polar, which is not polar at all, is HH. All right, be sure to look on page 430. Put it in your notes. It's a great picture. It basically has, like, that would be purely covalent being shared completely equally. Then you have the two atoms where this is a little bit negative because it's pulling that electron cloud, so this would be polar covalent. And then we're actually going to have all the way to ionic, where there's been a transfer of electrons, and this is ionic. So these are covalent, two nonmetals. This is ionic, metal, nonmetal. All right, when we draw a dipole momentum, what we do is we draw the bond, and you can draw the bond any way, and this is in three-dimensional space. And you look for the more electronegative ones. So carbon has a value of like 2.5, fluorine has a value of 4. The arrow goes toward the fluorine, you put a little Greek letter delta, and because the electron cloud has been pulled away from carbon, its nucleus is a little bit exposed, it's a little bit positive. Now N's the more electronegative one here, so just because it's right to left, it still works. Fluorine is the more electronegative one here. Look up the values, and that's going to be negative, and that's going to be positive. Okay, with ionic bonding, trying to visualize this, it basically just goes on and on and on until the crystal breaks off. So it can be a little crystal, a giant crystal, it just keeps going and going and going. Chemically bonded, plus minus, plus minus, plus minus. Cations are smaller because they lost an electron, and anions are bigger because they gained an electron. So for instance, our Na plus 1 would actually be smaller than just an Na, whereas a Cl minus 1 is actually going to be larger than a Cl because this has gained an electron. Covalent bonds, big difference here is that covalent molecules are individual molecules. So we might have a water molecule here, and it can be attracted to another water molecule, in fact it is, but that attraction right there is not chemical. All right, these are individual molecules chemically bound within the molecule, but not chemically bound to each other. All right, Lewis structures, we're going to, the next video is going to talk about covalence in Lewis structures. All I'm going to show you in this one is ionics, which isn't our huge focus, but it shows the valence electrons. So you need to have your periodic table out. You need to see the little numbers in parentheses. It tells you valence electrons. So with a Lewis structure, we look and we draw electrons in based on how many valence electrons. So sodium's in group 1, it gets 1. Chlorine's in group 7, so it actually gets 7. I'm going to draw them as little X's, so not to be confused. 7 valence electrons. Now, sodium will give up an electron to chlorine and thus become an Na plus 1 and a Cl minus 1, and then they will bond together. Now, if I had a Ca, that would have 2 valence electrons because it's in group 2. And if I were going to bond calcium with sodium, what would happen is that one of them would go to the Cl, but I would need another Cl with another 7 electrons here, and then that one would go here. So you'd end up with a Ca with a plus 2 and a couple of Cl minus 1s. You'd end up with a CaCl2. Here you'd end up with an NaCl. So those are ionic structures and transfers of ionics. Now the next one we're going to talk about is covalence.